the attack, in our opinion, a good attack, because you can spend, I don't know, 2 seconds to create a dictionary, and then you can come back whenever you want and just use the dictionary to gain access to the machine over and over and over again. So the exploit that we're going to show is basically, like I said, it's going to use DCE RPC over SMB. It will create a service on the remote machine, upload the file, start that file, that is an executable file, as a service, and that will basically connect back to us using the code that we use to grab a shell from the Windows machine. Now we have to wait. How much time do we have? Minutes, all right. Okay. So now this is like attacking a different machine or coming back to the same machine 2 days after we did the first stage of the attack, that is creating a dictionary. So we are gonna run the attack. No, but it was not correct. Did you log in? That's it. So basically what that part of the exploit did is start connecting over and over again against the server until the server returns one of the nonces that we have in our dictionary. At that point, the exploit sent back the response we got from the client. We gain access. Since this was a user with administrator privileges, we were able to start a new service that was actually our code, and that code connected back to us and gave us a shell. And that's it. So exploiting this vulnerability takes you 20 seconds, I don't know. And then, for example, we can leave and try again. That's it, it worked. That means that the server generated another duplicate challenge that we have in our dictionary. And you can do this like forever. You can reboot the machine again, even go to some other machine and try the same thing, and that machine will generate a duplicate challenge also.
Well, let's go with the prediction.
You wanted to ask something?
In all fairness, it looks like you have a firewall turned off.
And of course, you have to have SMB open, because this is exploiting a flaw in SMB. So
you remove a couple layers of defense.
No, but that's like saying, okay, I put the machine in the bottom of the river, it's safe. Now, what we are exploiting is a flaw that is present in a service that you need to use. If you are in a network, in an internal network, and you are sharing files among the company, it's very likely they're going to have the SMB service running. Of course, if you shut down everything and you don't provide that service, if you cannot reach service, you cannot exploit any kind of vulnerability in that service. But that's something that happens all the time. It's not something that we are removing layers. Where all vulnerabilities exploit a problem in a service that you are using. If you are not using the service, so you cannot exploit anything. Does that answer your question? You're not happy with the answer? But let's say that you have a flaw in SMB that is a remote buffer overflow. Just because you have the firewall app, that means that no one can exploit that? No, because if you actually want to use SMB, that everybody uses that because it's like the most common way to share files between Windows machines, also to access the registry, to do administration, to everything. You will need that service, and you can't just shut the service down.
Here you have the ability to execute code remotely. That's you can actually share your files without also allowing the code to execute, right? So
if you are an administrator, you can execute code, as I said that. And it's also the same thing with the SMB relay attack, with also known as the SMB credential reflection attack. It's also the same case. So that's a given. Yes, that's something that the user needs to have. Anyway, if you cannot execute code, you can still access the same files the user can access. And for example, you can download internal documents, I don't know, write things. If they have a share, you can actually write an executable file that's something that just hope for the user to click. Or you can download a file that has a .lnk extension and exploit some other flaw and things like that. So there's always a possibility to do something to exploit this vulnerability. Yes, there are certain things that have to happen, but these are things that are very well known and that pretty much all the attacks have into account and say that they need to actually execute code. But there are many ways to exploit the vulnerability. Basically, you are bypassing the authentication. So you can do whatever the user that you're exploiting can do. And that is bad. If it's an administrator, you can execute code right away. If it is not, you can access their files, modify their files, other things. Is that okay or no?
By the time you got it on a web page, you probably have everything you need in the first place.
All right. We can talk about it later.
Oh, so let's go.
So the other attack is the prediction attack. Basically, what we're doing here is we are trying to set the state of the PRNG on the vulnerable server to a state that we know. So basically, that is mimicking the memory of the remote machine. So we are simulating what the RTL random function does there, and we have the same thing that that machine has in their memory in our local machine. That is the internal state of the PRNG. Based on that, we can predict all the challenges that that machine is going to generate, because they know, again, the internal state of the PRNG. So now what he's going to do is, after we created a list of all the challenges that that machine could generate in the future, he's going to make one connection attempt to that machine, trying to perform NTLM authentication. And that machine will return a nonce. We can see in Wireshark the value of the nonce generated by the server. If we are able to expand that window. There you go. So the nonce is referred to as the encryption key by the code itself that is vulnerable, by Wireshark, and by some other specification documents. It's not an encryption key, it's a nonce, but they refer to that number as an encryption key. Just saying that because it is not an encryption key. So basically, this is the file that we generated by predicting the remote state of the PRNG. And basically, were you able to see what he did or no? Yeah. So basically, he grabbed the number that the machine, we made a connection, the machine returned a challenge. And we grabbed that challenge and looked for that challenge in the list of challenges that we predicted the machine was going to generate. And we found it. So basically, the attack worked. We can predict the pseudo-random numbers, or the challenges, actually, that the machine is going to generate. And we can use that to do the same kind of attack that we did with the first attack where we executed code. So does anyone else agree with what he was saying, or is just him? Yeah, go ahead. Yes, the original advisory already had all the exploit code. It was not executing code, it was just writing a file in some directory. And this is a rewrite done in Java, and yes, we are going to provide that. Yeah, on the internet. No, no, sorry about that. I don't know. I put some message in some mailing list, or you can give me your email, I can send you the link when it's available. Yes?
The technique of using an email script to force the victim to do SMB challenges, presumably that requires that you don't have SMB blocked with a firewall.
Yes. Most likely, this will be exploited in your internal network, not over the internet. The same thing happened with SMB relay or SMB credential reflection, but yes, that's the most likely scenario. That's correct. Yes?
You said the challenges were the same on computers started. Are they the same on every single computer, or does that change on the different domains?
Almost. I mean, actually, to try to explain that, we need to explain a lot of things that we have to explain how we kind of have to do like a cryptanalysis of the whole McLean-Marsiglia system, and we're kind of done like half the work that is needed. And we can tell you a lot of things, like, for example, some of these things are in the conclusions. One thing is that the function the the seed used by the Maglare-Marsaglia system is reseed every time that you make the connection, and also you can add the fact that, that's bad, because usually the code is using the same seed more than once, because they are using the current system time, and when they use the current system time, they actually, for example, have two calls to get the current system time. One is the call that is used to return in the packet that we mentioned, the SMB packet, the current system time to the attacker, and inside the get encryption call, they have another function. But because of the resolution of the timer, and because this is a multi-threaded, we think, server, the value returned by those calls is the same. So that's why they are leaking the time. It also has to do with the way the Maglare system works and a lot of things that we can talk about it in the hallway if you want, but it is possible that you can also, and since we can predict and we can set the internal state of the PRNG to whatever state we want, we can practically force any machine to return the challenge that we want. So, okay. So basically, how much time do we have? A minute? Okay, that's fine. So basically, in summary, like I said, what we found is, I think it's a big deal. I mean, from a technical standpoint, at least, I don't care about the hype or anything like that. When we found that, it was like, I can't believe this is happening, because it was like, I said the one thing that it should not be failing in the protocol, and it was failing. And that to us was very interesting. And from all the attacks that we showed, the passive replay attack and the active replay attack, although I think they are very efficient, because you saw that to exploit the attack, it took us, I don't know, seconds, not even a minute, you can actually improve that more. For example, instead of gathering 8,000 challenges, you can gather less challenges. You can also combine the prediction of challenges and only gather one challenge. You can do a lot of things if you put the time into actually making the attack better. We didn't do it first because we have a limited amount of time to spend on this, and then because we think that the attack that we have is efficient enough. About the prediction attack, like I said, basically what I was going to say here is what I said to him, is all the things about the fact that the server is leaking the current system time, and that current system time is used by the PRNG to generate the seed. Also the fact that the seed actually is only 2 bytes long, and then it's kind of expanded to 4 bytes, but in reality the entropy is only 2 bytes. That is also a bad thing, and all those things, and also the use of the Maglare-Marsaglia system that can be questioned, because it's not like something you would use to do that. Perhaps that is because that code was written in '93.
Imagine as an improved LCG. So
right.
It's from
LCGs context. Are known to be not suited for cryptographic purposes. So the fact that the Maglare-Marsaglia system is using an LCG is something weird that you better not use it. I mean, we actually bought the paper that was explaining how the Maglare-Marsaglia system worked, and it was written in a yes. But
they were also proposing using a table of random numbers. So
yeah, but the paper that explains the algorithm is written in a typewriter, and it says that one of the pros of the algorithm is that it uses like only one card or